This is the walking talking mock for combined science higher physics. As we go through this paper, make as many notes as possible. I will explain my thinking, I'll explain some extra information now and again, which may or may not get you marks, but it will help you answer similar questions. And after we finish, there is extra practice in this for you to complete. So let's start with the first question, which is question 5. So Alex is cycling up a hill, as shown in the diagram. The mass of Alex and the bicycle is 95 kilograms. At the top of the hill, the gravitational potential energy store of Alex and the bicycle has increased by 7,600 joules. So as he goes up, GPE, gravitational potential energy, increases. And if he were to come down, obviously the GPE decreases. So calculate the height at the top of the hill. Now they've given you the equation here. If they don't, where do you look? You look on the formula sheet. I know it might be obvious to some of you, but it's not obvious to everyone. The equations are given to you this year. Look at them on the formula sheet. So in symbols, we've got GPE equals M times G times H. GPE is 7,600. Mass is 95. G, gravitational field strength, is 10, and height is what we're trying to work out. So our next line of working is 95 times 10 is 950, times by height. We want to make height the subject of the equation, so we need to do the inverse of times by 950. So 7,600 divided by 950 gives us our answer. Type that in our calculator, and we get 8 meters. Alex transfers 9,000 joules of energy to reach the top of the hill. Explain why the amount of energy transferred by Alex is different to the increase in gravitational potential energy store. So the GPE increases by 7,600, but the total transferred is 9,000 joules. So where is that difference in energy going? So some energy is transferred to the thermal store. Now if you stopped here, you're going to pretty much guarantee to get a mark. It's always some energy is wasted as heat. But it is 3 marks, so we need to give 3 relevant points. So some energy is transferred to the thermal store of Alex's muscles, because anytime you do exercise, your muscles are wasting a significant amount of energy in the form of thermal energy. Alex also does work against. So what does this word work mean? Work is another word for saying energy. He transfers some energy against the force of friction. So there is going to be friction in the pedals, in the gears, in the wheels. Alex also does work against the force of friction, so more energy is transferred to the thermal store of the, you could say the bike or the surroundings, because the bike will heat up, but then that will then heat up the air in the surroundings. Now, sometimes they say explain how you can reduce that energy loss. If you wanted to reduce the energy loss, you would lubricate the wheels or the gears using oil. So that's not a question here, but that is very often a follow-up question. Right, part 3, calculate the efficiency of Alex to get to the top of the hill. So I will always write down efficiency is useful energy over total energy. And what do we know? It should always be less than 1. If you ever get an answer more than 1, you've made a mistake. So the useful energy, well, we're trying to get higher, so we're trying to increase the gravitational potential energy. So the useful energy, 7,600. The total energy is what Alex actually transferred, and it says 9,000 joules. So 7,600 divided by 9,000 is 0.84. Now I could, if I wanted, do 0.84 times by 100 is 84%. That is fine, but this is also fine. You're allowed to give your answer as a decimal. Part B, Alex goes back down the hill without pedalling. Calculate the maximum speed Alex can reach. Assume no energy is lost going back down the hill. Now obviously this is not true. There will be energy lost because of air resistance and friction, but we are told to ignore it. So we need to use this equation. So I'm going to write this out in symbol form. E equals 0.5 times mass times speed squared. Really easy to mess that out. Which energy do I use? So Alex is going down the hill. He's decreasing his height by this much. So this gravitational potential energy that he gained is what is going to be transferred back into kinetic energy, not this 9,000. Some of that's gone into his muscle, some of that's gone into friction, going up the hill, but that's not happening going down because he's not pedaling, he's just letting gravity pull him down. So this is 7,600, 0.5, the mass is 95, and it's velocity squared. So 7,600 is 47.5, so I'm multiplying those two together, multiplied by v squared. I want to make v squared the subject of the equation, so divide through by 47.5, which is v squared. 47.5, which is 160, so v squared is 160. I want to make v the subject, so I do the inverse of square, which is square root. So the square root of 160 is 12.649, and I'm just going to double check the question because it did say, which I thought it did, 1 decimal place. So 12.6 is what I write on my answer line. Okay, part C is 4 marks. So there's a good chance that there's going to be a couple of things we need to do. Alex buys an electric bike which assists pedaling by supplying 11 amps of current from a 24 volt battery. It takes Alex 30 seconds to reach the top of the hill. A total of 9,000 joules of energy needs to be transferred by Alex and the battery to reach the top of the hill. Calculate the energy supplied by the battery and use this to calculate the energy that Alex needs to supply by pedaling. And then it tells us we've got 2 equations. Power is current times potential difference, and we've got power is energy divided by time. So I'm just going to pause the video here and give you a few seconds to think this through, and then I'll obviously work it through for you. So quite a tricky question. So we have to note we want the energy supplied by Alex, and this 9,000 is the energy supplied by Alex and the battery. So 9,000 joules is the energy from Alex plus the energy supplied by the battery. So this is going to be our final step to work out just the energy supplied by Alex. So how do we work out the energy of the battery? Well, we've got these 2 equations. We've got the power, which we can easily work out. So the power of the battery is going to be 11 multiplied by 24, but that doesn't give us the energy. The energy is found by using this equation. So energy here is power times time, and power is I multiplied by V. So power is I multiplied by V, and then energy multiplied by time. So the energy of the battery is the current multiplied by the potential difference multiplied by the time. So 11 times by 24 times by 30. So 11 multiplied by 24 multiplied by 30, which is 7,920, but that is just the energy of the battery. We want the energy of Alex, which is 9,000 minus the energy of the battery. 9,000 minus the energy of the battery, which gives us 1,080. So it's always got to do things in symbols first and get one overall equation. But if for any reason you struggle with this or you're a bit confused, you can work things out individually. It's just always a good idea to keep things separate. So for example, maybe under this equation you work out the power. Under this equation you can then use the power and the time to work out the energy, and then somewhere else you write down the final step. D. Alex says, if I cycle more slowly, I will use less power to reach the top of the hill. Explain why Alex is correct, and it's 3 marks. So it probably makes sense to just really be clear what power is. Power is the rate of transfer of energy or energy over time. So we're just copying this out. So what happens if we make the time smaller? So if I cycle more slowly, so cycling more slowly increases the time. So will that make the power go down? Well, in order to know that, we need to know what happens to the energy. Now, does the hill change its height? No. Does therefore the amount of GPE you need to get to the top of the hill change? No. So the energy required stays the same because the hill is the same height. So we have this is the same. So therefore, if this goes down, the power also goes down. So the power does go down. So between this and these 3 points, that should be more than enough to get the 3 marks. Okay, question 9. I am going to let you have a go at. We are going to do this question 4. So different types of wave can be used for communications. 50 years ago, microwaves were used for long distance communications. Microwaves travel through the air between microwave aerials. Now, light waves travelling along optical fibres are normally used instead. So if you don't know what these are, don't worry too much. You don't need to know much about them in order to answer this question. But you've probably heard of fibre optic broadband. So that is glass cables. The light travels inside, reflecting off the sides, and transfers the signal. So compare and contrast microwaves and light waves. So compare could mean difference, but it probably means the same here because contrast definitely means difference. So what do we know? What is true about both of them? They are both electromagnetic waves, which means they both travel at 3 times 10 to the 8 meters per second in a vacuum. What else? Well, they're obviously both transverse waves because they're both EM waves, and all EM waves are transverse. But what is different about them? Well, microwaves have a longer wavelength. So they are much longer waves than light waves, which means they have a lower frequency, and it also means they have a lower energy. Now, you don't need to put all of that for 2 marks, but there's lots of information there that we need to know. So the next one says calculate the speed of light waves in an optical fibre. So we should know that the speed will decrease when it enters an optical fibre, and this is an example of refraction. So the optical fibre is more dense, therefore the light wave slows down. So what have we been given? We've been given the speed, we've been given the time to travel 90 kilometers. So we've also been given a distance. So using the data sheet or just from memory, we should know that speed equals distance over time, but it's 4 marks, so there's probably some extra tricks here. So let's look at the speed. So the speed, well, we're trying to work that one out. The time, so time to travel 90 kilometers and microseconds. So it's 450 microseconds. So micro means 10 to the minus 6. So times 10 to the minus 6. Very, very common in waves. It's also very common in biology, particularly microscopes. And the distance, 90 kilometers, so 90 times 10 to the 3. So now our distance over our time is this divided by this. So 90 times 10 to the 3 over 450 times 10 to the minus 6. So I'm going to do it as a fraction just so I don't make any mistakes with my conversions. And I've got this here. Now it makes sense to give this a standard form. So that's 2 times 10 to the 8 meters per second. So does that make sense? Well, we said it should slow down. It was 3 times 10 to the 8, and now we've got 2 times 10 to the 8. If you ever get an answer greater than 3 times 10 to the 8, you are wrong, because waves can never travel faster than that speed. Okay, part II. An engineer suggests using an optical fibre made using a new material. In this new material, light waves take 432 microseconds to travel 90 kilometers, and I'm just going to write here the old material, it was 450 microseconds. Calculate the percentage decrease. So you do this a lot in chemistry when you're looking at change in mass. You do this a lot in biology when you're looking at, for example, osmosis, the uptake of water or the loss of water. So very, very common question. So percentage decrease is the change in, not change in mass, it's going to be the change in time over the original time. So the change in time is 450 minus 432. The original time is 450, so that's 18 over 450. Put that in your calculator, you get 4%. Now you might say, hang on a second, have I forgotten about the microseconds? Well, sort of, but actually it doesn't matter, because I've got a microsecond here divided by a microsecond here. They would cancel out, so there's no difference, there's no need to convert it. You can if you want, but there's absolutely no need. Part III, the new material will be 10% more expensive than the old material. Suggest why it's not worth using the new material. Use your answer to the previous question. So that's fairly easy, we're comparing 10% with 4%. So the cost increase of 10% is 2.5 times greater than the saving of 4%. So although it's 4% faster, and maybe we can transfer, I don't know, 4% more data, costs us 10% more, so obviously not a sensible trade-off. Okay, question 5 is for you to try. On the next page, this is just a mistake, this should not be here at all. Cross this one out, the one that starts with stars. If you turn over another 1, 2, 3 pages to the one that is about a transformer, we're going to start with this one. So Sarah and Jamal are investigating transformers. They build a model transformer using an iron core and 2 lengths of insulated wire. So we've got our input potential difference, and it is AC. AC stands for alternating current, which means that the potential difference is always going positive to negative. That's really important. Transformers need AC to work. We've got a voltmeter and an ammeter to measure the potential difference and the current. The voltmeter is put in parallel. The ammeter is is put in series. We've got 120 turns round the primary side, so the primary coil is the first coil, and then we've got 800 turns round the secondary part of the transformer, so the secondary coil. And then that our output, this will also be AC output, so the output will also be like this. And we've got 120 turns here, we've got more turns here. So what is this doing? This is a step up transformer, which means the voltage or the potential difference increases and the current will decrease. So it says the actual readings on the meters are as follows. Calculate the input power. So power equals current times potential difference. The input, this is the input side, so V1 and I1 is what we want. So we want the input, which is 14 amps, multiplied by the input potential difference, which is 2, and that is obviously 28 watts. The fact you get 3 marks for this is really quite generous, but there you go, occasionally you do get some nice easy marks. Calculate the efficiency of the transformer. So efficiency is, well, we said earlier it's useful energy over total energy, but you can also write it in a different way. You can also say it's useful power over total power. And why is it okay to say that? Well, power is energy over time. So if we say this is useful divided by the total, that's the same as saying energy useful divided by energy total divided by the time, and then this time would go on top, because if you divide by a fraction it's the same as timesing by 1 over that fraction, so these times actually cancel, so you just end up with energies. So this is entirely fine to use. Now we've just got one extra thing to note. We look at our answer line, we see it's a percentage, so actually they do want us to multiply by 100 here. So you always need to check the answer line, because if we look earlier on, going back to the very first question, there was no answer line, there was no percentage, which meant it was fine to give your answer however you wanted it. So our useful power we already worked out was our useful power we haven't worked out. We've worked out the total power because that is the same as the input power. So the output is the useful. The output is, so the input is total. That's what you put in, and that's what you get out. So we've worked out the input, which was 28 watts. The output, we need to see what we get out. So the output current multiplied by the output potential difference. So that is this multiplied by this. So 2.2 multiplied by 11.8. If you are unhappy that I've skipped a step, I could break it down. I could say that the output power equals I2 multiplied by A2, which is 2.2 multiplied by 11.8. So let's just type that all in our calculator. 2.2 multiplied by 11.8, and then times by 100 as a percentage, and I get 92%, and that is less than 100, which is really helpful. If it was more than 100, I've definitely made a mistake. So why is it not 100% efficient? Because we usually assume that transformers are. So pretty much the same answer as always with electrical circuits. Some energy is wasted as thermal energy as the wires, or you could say the iron core, heats up. So the wires will heat up because there's current going through them. The iron core will heat up because there's actually a magnetic field going through it, and a very small amount of heat will be generated. And if you've done this practical, transformers also vibrate. So it would also be correct to say some energy is transferred away as sound waves as the core vibrates. Okay, the next question I'm going to allow you to do. We are going to skip a couple more pages to question 3 here. So Kareem wants to use solar energy to provide electricity for his house. He fits photovoltaic solar panels to his roof. These solar panels use energy from the sun to generate electricity. Which 2 statements are correct about solar panels? Solar panels generate more electricity when it's sunny. This is obviously correct. Solar panels generate more electricity at night. Well, that is obviously wrong. Solar panels generate all the electricity needed. Well, absolutely not. They probably generate, I don't know, anywhere from 0 to maybe 15% in the UK, roughly. Solar panels release carbon dioxide. Well, no, that is not true because they are renewable. And solar panels use a renewable source of energy. I mean, this is true. Technically, the sun will run out eventually, but not in our lifetime. So we do class solar panels as renewable. 3b, the total energy transferred from the sun to one of Kareem's solar panels is 200 joules. So this is the total energy. The useful energy is 32. The rest of the energy is transferred to the surroundings as thermal energy. Calculate how much energy the solar panel transfers to the surroundings. So that's really easy. 200 minus 32 is 168 joules. Very easy. Kareem draws an outline of a Sankey diagram for the solar panel. So total energy transferred from the sun, 200 joules, and then we've got what is useful and what is wasted, or sometimes they're the other way around. So transfers to the surroundings, this would class as wasted. So this would be 168 joules to the surroundings. And the useful would be 32 joules, which would be transferred electrically. You don't get these very often, just a way of representing useful and wasted. Usually they're to scale. So if they ever kind of ask you to do calculations, just remember they're to scale. So this would be 32 out of 200, and this would be 168 of 200. Sorry, this here would be 168 out of 200. Okay, we're going to skip ahead to question 9 that has this table on it. So it says, complete the nuclear equation for the decay of the uranium isotope into an isotope of thorium. And we've got this information in the table. So uranium, a type of emission is alpha. That's really important. And alpha is a helium nucleus. So it has 2 protons and 2 neutrons. So it is 4, 2. And that means we can immediately write in here alpha, 4 and 2. And we need to make sure that the top half of the equation, so the mass, is the same on both sides. So it's 234 here, it's 4 here, so that must be 230, because 230 plus 4 equals 234. And we must make sure the bottom half, so the proton number, or the atomic number, stays the same. So it's going to be 90 here, because 90 plus 2 equals 92. Supposing the question was carbon 14 decays to something plus something, how would we do this one? So we would look up carbon, we'd see it's beta, which is a fast moving electron. We would know that it's 0 because there's 0 protons and 0 neutrons, and minus 1 to represent the charge of minus 1. So the beta particle is 0 and minus 1. The top numbers, the atomic mass, we must balance. So it's 14 over here, 0 here, so it must be 14. And the bottom, the proton number, it's 6 on the left-hand side, minus 1 here, which means it is 7 here. I'm being attacked by a cat, I do apologise. Okay, on with the questions. BI, a woolly mammoth was discovered in a melting glacier. The net decline of 14.6 emission of the mammoth was recorded as a quarter. Calculate how long ago the woolly mammoth died. So really easy if we use a table method. So we're going to have columns for time, number of half-lives, and fraction. Now the time always starts at 0, number of half-life starts at 0. What fraction do we start with? We always start with 1. Now why have I put fraction here? Well, because my answer has been given as a fraction. If it was a mass, then I would cross this out and put mass. If this was activity, I'd cross this out and put activity. So the number of half-lives, we're always going to go 1, 2, 3, and so on. The fraction is 1. After 1 half-life, it's gone down to a half. After 2 half-lives, it's gone down to a quarter. After 3, it would go to an eighth, and so on. Now it tells us we can stop at a quarter, so we only actually need to go until here. So that just leaves us with our time. So use information from the table. We can see that for carbon 14, it has a half-life of this long. So after 1 half-life, it will be 5.73 times 10 to the 3. After 2 half-lives, it will be 2 lots of 2.73 times 10 to the 3, which is, I think it's 11,600 years ago. Suggest one reason why the value calculated here is likely to be inaccurate. So the most obvious one, radiation is, or maybe not radiation, radioactive decay is random, so the kind of count rate will vary. Now you could talk about background radiation making it also inaccurate, but I think this is the most obvious one. You know, we tend to think of the count rate doing this, but actually it'll never do exactly that. It always jumps a little bit, so the count rate might do, you know, something like this, but over time, on average, it follows that nice curve. Okay, we're going to skip now to our final question, which is question 7. So this diagram and this table. So it says a radioactive salt emits ionizing radiation. Complete the table to show which materials absorb alpha radiation. Tick at least one box. So what absorbs alpha? So paper will block it and absorb it. Aluminium will also block it and absorb it. Thick lead will also block it or absorb it. Beta, we can see, will get through paper, but it's stopped by aluminium, stopped by lead. Gamma will pass through paper, aluminium and lead. If it had air, for example, what absorbs alpha? We are talking about centimeters of air. Beta, we're talking about meters of air, and gamma is close to infinite in air. So a bit of extra information there. What else would absorb alpha? Skin would also absorb alpha, and that's quite a common one when we're talking about medicine. So what's going on in this question? Kareem uses the equipment shown in this figure to investigate how different absorbing materials affect the amount of radiation received by a detector. So the source is here, the radiation comes out, the material will absorb it. Sorry, I was attacked by a cat again. And then the detector here will detect it. So the radiation detector is called a Geiger-Müller tube. So sometimes they will use this rather than just a radiation detector. This is Kareem's method. Measure the count rate with no absorbing material. Measure the count rate with different absorbing materials placed between the source and the radiation detector. Kareem plots his result on the bar chart in figure 7.2. Which type of radiation or radiations does the source emit? So let's just quickly look at this. Measure the count rate with no absorbing material. So this will obviously detect all of the radiation. And then here, some will be blocked. All right, and we can use the information in this table to see what is happening. So, with no material, we're on about 47 counts. With paper, it's actually gone up a little bit. So why has it gone up? Well, it's gone up because there is background radiation. And it's gone up because the decay is random as well. So if you do it any 2 times, you will get a different number of counts. And if you do it a couple of times, you will also get background radiation that will come. So this is the Geiger-Müller tube. This is the absorbing material, and this is the source. Even if we block it all from here, it's possible that some background radiation will get into the tube and be detected anyway. And where does this come from? Backgrounds come from things like cosmic rays, so that's space. It comes from food, so bananas are one example that are quite radioactive. It comes from C14, so we looked at that in the previous question, which is found in anything that's living. So even us right now, we have some radioactive elements or isotopes of carbon-14, and there are other sources like the radioactive sources in the school, the power stations, very small amount, very small amount, nothing to be scared of, gets emitted. If anyone smokes, then there's a lot of radiation in the nicotine leaves, so some of that makes its way into this detector as well. So that's why it goes up. So from no material to paper. Now when I answer this, I'm not really going to answer this in full sentences. I'm just going to answer this in kind of sort of bullet points, sort of sentences, just to make it really easy. So no material to paper, there is no drop in count rate. So this rules out alpha, because alpha should result in a massive decrease. And then when aluminium is added, what happens? There is a significant drop in count rate, which suggests, or suggesting, that beta is being emitted. All right, because obviously aluminium from the table on the other side blocks beta.